Okay, here's a question for you. What do a glass of milk, a puff of smoke, and a bowl of jello all have in common? I know, they seem totally random, right? But believe it or not, they all belong to this secret category of mixtures that's pretty much hiding in plain sight all around us. So let's dive in and explore this hidden world. First, let's do a quick recap of the two types of mixtures we all remember from science class. On one hand, you've got suspensions. Think muddy water. It's cloudy, it's got big, chunky particles, and if you just let it sit, all that mud is going to sink to the bottom. Then you've got solutions. Think salt water. The particles are teeny tiny, it's totally clear, and that salt is never ever going to settle out. Simple enough, right? Well, maybe not. Because then you get to something like milk. It's cloudy and opaque, for sure, just like a suspension. But have you ever left a carton of milk out and seen all the white stuff just fall to the bottom? No way! It stays perfectly mixed. So it's not a suspension, but it's definitely not a clear solution either. So what is going on here?
Well, the answer is that it's this third kind of in-between state of matter. And this is the amazing world of the colloid.
So what is a colloid? You can think of it as the best of both worlds. The particles inside are way bigger than the tiny molecules you'd find in a solution, but they're still so small and light that gravity just doesn't affect them. They refuse to settle out, just staying suspended forever. And that's the secret to that stable, cloudy look you see in milk. And you know, that cloudiness has a specific cause. It's because the particles are the perfect size to scatter light. It's a really cool phenomenon called the Tyndall effect. You've definitely seen this before. If you've ever driven through fog at night and seen your headlight beams cutting through the air, that's it. The light is literally bouncing off all those tiny suspended water droplets, making the beam visible. And a little bit of trivia for you. The name itself is pretty neat. It was invented way back in 1861 by a chemist named Thomas Graham. He took the Greek words for glue and like, because the first colloids he was really studying were things like gelatin and starches. You know, stuff that was very glue-like. Okay, so now that we know what we're looking for, let's check out just how common these things really are. And trust me, once you see it, you're going to start noticing them absolutely everywhere. So colloids come in all different flavors, depending on what's mixed into what. The thing that's being suspended is called the dispersed phase, and what it's floating in is the dispersion medium. For instance, if you suspend a liquid in a gas, you get an aerosol, like fog or clouds. If you mix a liquid into another liquid, you get an emulsion. Yep, that's milk and mayonnaise. You can even bubble a gas through a liquid to get a foam, like whipped cream, or trap a liquid in a solid to make a gel. The possibilities create this huge, diverse family of mixtures. So let's bring it back to our first example. Milk! It's a textbook emulsion, just tiny little drops of liquid butterfat floating around perfectly suspended in water. And our Jell-O? That's a gel. It's mostly just water, but all that water is trapped inside this intricate, web-like structure of solid protein. That's what gives it that classic jiggle. And that fog we were talking about, the one that shows our headlights? An aerosol. Just countless microscopic droplets of liquid water hanging out in the air. See? I told you, they're literally everywhere. So, okay, colloids are everywhere. That's cool. But what can we actually do with them? How do we use their unique properties? Well, for one of the best examples out there, we just have to look at something we all use every single day: soap. The entire magic trick of soap comes down to this one word: amphiphilic. It just means the soap molecule has a split personality. One end is hydrophilic, which means it absolutely loves water. The other end is hydrophobic, meaning it hates water and would much rather hang out with oil and grease. So here's how it all works. When you wash your hands, the soap molecules go to work. The water-fearing tails immediately dive in and grab onto any grease or oil they can find. At the same time, the water-loving heads stay on the outside, holding on to the water. What you end up with is a tiny little sphere with the grease trapped inside, and this whole package becomes a brand new colloidal particle, suspended in the water. And then, it all just gets washed right down the drain. Pretty clever, right? Now, this whole idea of grabbing tiny particles and keeping them suspended, well, it's useful for a lot more than just doing the dishes. The science of colloids has been used to tackle some absolutely massive industrial and environmental challenges. Let's talk about smoke. Smoke is just a colloid of solid soot particles suspended in a gas. And it turns out those little particles often carry an electrical charge. So in the early 1900s, this chemist, Frederick Cottrell, had a brilliant idea. He invented something called an electrostatic precipitator, which is basically a device with these highly charged plates that attract the colloidal smoke particles like a magnet, pulling them right out of the air before they can pollute the atmosphere. It was a game changer, and we still use that technology today.
Now, let's jump ahead about 100 years to a massive environmental disaster. In 2010, the Deepwater Horizon oil rig explosion released an almost unbelievable amount of crude oil into the Gulf of Mexico. The final estimate, 4.9 million barrels. Just trying to imagine that much oil it's staggering.
So how did they fight it? Well, they fought it with colloids. Responders used almost 2 million gallons of chemical dispersants. And these dispersants are basically just powerful emulsifying agents. They work exactly like the soap on your hands. Their job was to break that enormous oil slick into zillions of tiny colloidal droplets, creating a massive oil and water emulsion. Now, this doesn't make the oil vanish, but by dramatically increasing the surface area, it allowed naturally occurring bacteria in the ocean to start digesting and breaking down the oil way, way faster than they ever could have otherwise. So you see, from the milk in our cereal to cleaning up our planet's biggest messes, colloids are one of the most vital and versatile types of mixtures there is. They are that hidden in-between state that really makes so much of our world work. It makes you wonder, doesn't it? Where are we going to harness their incredible power next?